A deep dive into scikit-learn's Gaussian Process Regressor. The Gaussian Process Regressor in scikit-learn is a powerful tool for regression tasks, particularly when dealing with complex, nonlinear relationships between input features and target values. This model leverages the principles of Gaussian processes, a probabilistic framework for modeling functions, to achieve both predictions and uncertainty estimates. Here's a comprehensive breakdown. 1. The essence of Gaussian processes. Functions as random variables, unlike traditional machine learning models that learn specific parameters for a fixed function. Gaussian processes treat the underlying function itself as a random variable. This allows for inherent flexibility in representing complex relationships. Prior belief before observing any data. A Gaussian process assumes a prior belief about the function's behavior. This prior is represented by a mean function and a covariance function kernel. Posterior inference upon observing training data. The prior belief is updated to a posterior distribution, reflecting the learned relationship between inputs and outputs. This posterior distribution encapsulates both predictions and uncertainty estimates. 2. The Gaussian Process Regressor class in scikit-learn. Key parameters. Kernel, the core of the Gaussian process, specifying the covariance function that determines how closely related different input points are. Choosing an appropriate kernel is crucial for model performance. Several predefined kernels are available in scikit-learn RBF. Matern, rational quadratic, dot product, etc. And users can also define custom kernels. Alpha, the noise level assumed in the data. This parameter helps in regularizing the model and avoiding overfitting. N restarts optimizer controls the number of random restarts for the optimization process used to find the best kernel hyperparameters. Optimizer specifies the optimization method for finding the best kernel hyperparameters. Random state ensures reproducibility by fixing the random seed used in optimization. Key attributes. Kernel, the fitted kernel after optimization, representing the learned covariance function. Log marginal likelihood value, the log marginal likelihood of the fitted model, providing a measure of how well the model fits the data. 3. Workflow with Gaussian Process Regressor. 1. Data preparation. Prepare your training and test datasets, ensuring appropriate scaling and handling of categorical features. 2. Kernel selection. Choose a suitable kernel based on your prior knowledge about the underlying function. Consider the smoothness, periodicity, and overall shape of the expected relationship. Experiment with different kernel options and their hyperparameters. 3. Model instantiation. Create an instance of Gaussian Process Regressor, specifying the chosen kernel and other relevant parameters. 4. Model training. Fit the model to your training data. Using the fit method, the model will learn the optimal kernel hyperparameters by maximizing the log marginal likelihood. 5. Prediction. Generate predictions for new input points using the predict method. 6. Uncertainty quantification. Access the uncertainty estimates for your predictions using the predict methods. Returns TD argument. 4. Advantages of Gaussian process regression. Nonlinear relationships. Excellent for modeling complex nonlinear relationships. Uncertainty estimates. Provides inherent uncertainty estimates for predictions, crucial for decision making and model validation. Flexibility. Allows for a wide range of kernel choices, offering adaptability to different data characteristics. Smoothness. Generally produces smooth predictions, reflecting the inherent smoothness of Gaussian processes. 5. Challenges and considerations. Computational complexity can be computationally expensive for large datasets, particularly during training. Kernel selection. Choosing an appropriate kernel is crucial and requires domain expertise and careful experimentation. Overfitting. Susceptible to overfitting if the kernel is too complex or the noise level is underestimated. 6. Real-world applications. Robotics. Modeling robot trajectories and predicting robot behavior. Finance. Forecasting stock prices and analyzing financial time series. Machine learning. Creating surrogate models for expensive simulations and optimizing complex functions. 7. Example code. Python. Import numpy as np. From sklearn, Gaussian process. Import Gaussian process regressor. From sklearn, Gaussian process, kernels. Import rbf. Generate some synthetic data. np, random, seed 0. xnp, sort 5. np, random, rand 20. 1. Axis 0. ynp, sin x, ravel. Create a Gaussian process regressor with rbf kernel. Kernel 1.0 rbf length scale 1.0. Length scale bounds 1e-2. 1a2. GPR Gaussian process regressor kernel. Random state 0. Fit the model to the data. GPR. Fit x, y. Make predictions and get uncertainty estimates. Xtest np, linspace 0. 5. 100. np. New axis. ypred. ystd GPR, predict xtest. Returns td true. Visualize results. Import matplotlib, pyplot as plt. plt, plos. y. r. Label training data. plt, plostest. ypred. b. Label prediction. plt, fill betweens test. 0. ypred, ystd. ypred ystd. Alpha 0.5. Colab. Label uncertainty. plt, legend. plt, show. This detailed explanation provides a comprehensive understanding of the Gaussian process regressor in scikit-learn. Remember to carefully choose your kernel, tune its hyperparameters, and consider the computational complexity for your specific application. By utilizing this powerful tool, you can gain valuable insights into complex relationships, make informed predictions, and quantify the uncertainty associated with those predictions.